this narrowband IoT. So if you take narrowband IoT, so here this is the base station. So the base station, around the base station, so IoT devices are going to be spread everywhere. So in the standard, so they consider 3 regions. So the red region and the green and the blue. So how they identify a particular device, IoT device, whether it is in red or green or blue, how they identify is, so the device send a signal to the base station. Once the base station receives the signal, based on the signal power level, it will identify whether it is in red or green or blue. Depends on the received signal strength. So here we are going to have, so if the received signal power is greater than this threshold, so it is in the red region. If the received signal power is between this and this, it is in the green region. So if it is less than this one, it is in the blue. So if the IoT device is far away, the received signal power strength is less. So by that way, the base station knows that, okay, how many devices are in this red, how many devices are in green, how many devices are in blue. Say here, all the devices send the signal to the base station. So then base station estimates the signal power. Once it estimates the signal power, so it knows that, okay, 10 devices within this red region. Yeah, blue region, so within the cell region, in the cell boundary. So by that way, the whole devices around the base station are going to be in with these 3 regions. So now for every region, so this base station is going to inform 3 parameters to use it to transmit the data from the device to the base station. So resource configuration, the base station inform 3 parameters for each region. So what are those 3 parameters? So one is the number of preambles. So number of preambles means, so preamble is a sequence, a sequence. So from the preamble pool, so every IoT device select one of the preamble and send to the base station to establish the connection. So now the question is, so limited preambles are there. For example, if you have 50 preambles pool. So in the 50, so you are say if you have more devices. So if there are 30 devices in this red region, so in this 50 you have to allocate 30 or 35 to the red region because more IoT devices there. So now say for example, all the, say 40 devices are in blue region. So more number of preambles will be assigned to the blue region. So number of preambles should change dynamically. Say if you take one frame, so transmission time intervals, for example, 600 millisecond, 0.6 second. So within that 600 millisecond, how many preambles were allocated for blue, red, green? So next 600 millisecond different. So that means dynamically the number of preambles will have to be changed because the users will move from red to green, green to blue because of mobility. So every 600 millisecond, the number of devices in these 3 regions is going to change. It's not fixed number. So because devices will move. So the number of preambles should vary every time frame. Another one is, another parameter for these 3 regions, the repetition value. So one preamble, you are going to repeat certain number of times, power of 2. So say for example, this device, red region, this device, it is selected one preamble. It is going to repeat 4 times or 8 or 16 or 32 up to 128 power of 2. So it is going to repeat because, say for example, if you take in this blue region, so it's far away, this is low power wide area network. So then what will happen? So power level is very low. So then you have to increase the repetition, then only it will succeed to establish the connection. So if it is in the red region, so repetition factor 2 is enough because the power is high. So therefore, the repetition value should be one of the power of 2 up to 128, 2, 4, 6, 2, 4, 8, 16, 32, 64, 128. So one of the value should be allocated for each region, base station. The other one is going to be the number of random access opportunity. So that means number of random access opportunities is, so say one device now failed. It will be allowed to try again and again and again. So how many times it will be allowed to try again and again? So that is the random access opportunity here. So there are 3 parameters for red, 3 for green, 3 for blue. So if you take this example here, now you see the blue, the repetition factor is 8. So preamble repeated 8 times. So if you take green, preamble repeated 4 times, because the blue one far away. So far away means low power, repetition factor should be high. So red one is near to the base station, repetition factor of 1. This is just an example. So then if you take the random access opportunity, so within certain time, so here green, random access opportunity, here 1, 2 here. So if you take blue, random access opportunity 1, red 4, 1, 2, 3, 4 opportunities within the time frame. So there are 3 parameters for each region, total 9 parameters. So that means base station informed to the devices periodically broadcast. So these 9 parameters for every at the beginning of each time frame. No, this is an example. This is just an example. Because the random access opportunity, it varies. Because if the channel condition is very worse in this blue region, if it is very worse channel condition, so random access opportunity will increase. So these 9 parameters dynamically should change. Yeah. Yeah, it depends on the channel. Yeah, say for example, if more devices suddenly came, so then because of interference, so then you won't get the required SINR at the base station. So then it won't succeed. So therefore, the repetition factor should increase. This is just an example. These are not exact value. This is just an example. So now this is the narrowband IoT in the standard. So this 9 parameters, the source configuration is to be set. Now the question, so once here, so if you take, I told you narrowband IoT uses 1 resource block. 1 resource block is 180 kilohertz. If you take this 180 kilohertz here, 180 kilohertz is divided into 12. So that means 12 subcarriers. So that means each one is going to be 15 kilohertz. That 15 is divided into 4. So that means one subchannel is going to be 3.75 kilohertz. So what is happening here? This is one preamble. If you take this is one preamble. Preamble is transmitted using frequency hopping in 4 symbol group. So this is one symbol, this is another. So this is one preamble transmitted in 4 subcarriers using 4 symbol group. So by this way, we can enhance the coverage frequency diversity. Then if you have narrow band, so using the time of arrival, the localization purpose also. So that's what to enhance the coverage. So this repetition scheme with frequency hopping is used. Because you know, low power wide area network, the coverage region should be 15 kilometers, not human to human communication. So that's what here in the standard, they use frequency hopping. So frequency hopping basically, so one preamble is transmitted in 4 subcarriers, so 4 symbol group. So then this is the repetition factor 2. This preamble here repeated again here. It can be 4, it can be 6. So here if you see here, so this one transmission time interval, say for example this one here around 600 millisecond. So in this 600 millisecond, so here the repetition 1, 2, 3. So this is, so here the physical random access channel here. So here first 5.6 millisecond, so repetition 1, 2, 3, 4 like this. So the remaining is going to be the physical user shared channel. So this is the data transmission. So if you take this frame 600, roughly 600 millisecond, so 180 kilohertz. So during this time, the repetition of preamble. So once establish the connection, so then transmission of the data. So now uplink, yeah. The uplink shared channel. Yeah, U is for uplink. So this is the way that IoT devices transmit to the base station. So here this is the, sorry. So here I haven't considered anything about the channel estimation. That is a separate issue. Here, so one device, how to establish the connection with the base station and how to transmit the data. Yeah. This is at the MAC layer. Yeah. So here, so now this how to establish the connection, random access. So these are the step 1. So that is every device is going to choose one preamble. So once it selected the preamble, so here it is going to set a random access response window and wait for the base station to give the grant. So take the preamble and transmit and wait for this random access response window here. So then once the device establishes the connection, so then the radio resource control connection request, once the base station approved, so the RRC connection setup. So here once it's set up, then the remaining is going to be the data transmission. So this is the procedure for random access. So to establish the connection with the base station. So now we are going to have 2 problems we are going to have here. So what are the 2 problems that we are going to have? First one is the low SINR, because this is low power wide area network. So since this is low power wide area network, so SINR is very low. So if SINR is very low, then cannot be detected. So then we are going to have SINR outage. The second problem is going to be the collision, because here we are going to have thousands of devices, but number of preambles only 54. So 2 devices select the same preamble, so then we are going to have the collision we are going to have. These 2 are the main challenges. One is SINR outage, other one collision outage. These 2 are the main problem in the massive IoT, narrowband IoT. So now, if you see the, if you do if you see the numerical results by simulation, say when the devices are in the radius of 50 meter or 500 meter, then 1000 meter radius from the base station, then 1732 meter radius. If you see here, most of the channel occupancy, the green one, to establish the connection. So data transmission, the blue one. So data is small packet. So most of the resources are wasted to establish the connection. The reason is this one. So because of this SINR outage and collision outage, so most of the resources, the green, spent to establish the connection. Once established the connection, data transmission only the blue one. Very small packet of data in narrowband IoT. So now the main challenge is, so how to solve this random access problem here. So now, so we have done theoretical work and numerical work, and we found that, so when you increase the repetition value, the success rate high, random access. So here when you have repetition factor 8, so random access success probability is high. So this is the density of devices over density of base station within that area. Number of base station per kilometer squared is lambda B, lambda D, number of devices per square kilometer. So when you see here from these results, we found that if we increase the repetition factor, then the random access success probability is higher. So now we found that so within 10 attempts, 10 opportunities, so that means one device is allocated 10 times you can try, failed, second time, third time, within 10 opportunities when it is allowed, they will succeed 99% within 10 attempts if the repetition factor is 64. So that's what we found using the mathematical modeling. We found that if the repetition factor, I have included all the derivation, it takes long time. The conclusion is, if the repetition factor is 64, the device will succeed to establish the connection within 10 attempts with 99% probability. So to achieve 99% success probability within 10 attempts, in each attempt, the success probability should be 37%. So here we just consider only one region to see, so what should be the repetition factor. Repetition factor for each region vary. So here in this case, we haven't considered 3 regions. Just base station within a circle, we haven't considered 3 separate regions. Every region it will be different. So we just considered only one region, so that is with a certain radius. So the highest radius is the blue outside circle. Further distance, so this is the 64 is the upper bound. 64. So if it is red one, it is less. So the last one, if the repetition factor is 64, now it will succeed. Now the question is, we cannot fix 64 permanently. Why we cannot fix permanently? Because the environment changes dynamically. So the number of devices enter and leave every few milliseconds it's changing, few seconds it is changing. So therefore, we cannot have, okay, so 64 we cannot fix it. So it should change dynamically every transmission time interval, dynamically should change. If the channel condition is good, not necessarily 64, it should change to 16 or 32 or 2. So it cannot be static. So now the question is, so how we can change these parameters dynamically, not static. So if it is static, we take a long time interval and we fix the parameters. Okay, blue this, green this, red this. If we fix it, then we cannot achieve best performance because we are going to waste the resources. So therefore, so here we have to change dynamically. So dynamic optimization. So now here we have 9 parameters. So every region we have number of preambles, random access channel opportunity. Then we have repetition value. Then we have some other parameters also. What are the other parameters is, say, random access control scheme. Random access control scheme, for example, access class barring means, so each device is going to generate a random number between 0 to 1. So base station broadcast, okay, now those who generated a number greater than 0.6, now you can transmit. Say now you have 50 devices. Base station says that, okay, those who got, every device generated a random number between 0 to 1. So those who generated above 0.6, you can transmit now. Others, you cannot transmit now. By that way, they can control the collision. So if you have this ACB factor, back-off factor, and we have distributed queuing factor, there are two. So here, if you use this scheme, one parameter should be dynamically changed. Base station, ACB, the bar, so it should be not 0.6. It can be 0.4, 0.7, it has to change dynamically, depends on the load, number of users. So this number should be changed. So back-off factor, you know what is meant by back-off factor. So if failed, it will have to wait certain. Then if you use distributed queuing scheme, so there are two parameters. So I will explain later. So that means here you have 4 parameters. So now how many parameters? 9 plus 4, 13 parameters should be changed dynamically at the beginning of every time frame. So base station inform this. Now this 9 should be, these are the 9 parameters, not fixed. So we are going to have dynamic optimization. So dynamic optimization means, so what is the dynamic? Because here we cannot use the conventional convex optimization scheme, we cannot use it because environment is changing. Since environment is changing, we cannot use the conventional scheme because here model deficit, we don't have the model. So what is the solution? Only way is the machine learning. So that is the motivation to have the machine learning. Sorry? Yeah, I will come back to that later here. Yeah, so here back-off factor means, so once you fail, you will have to wait n time slots, you have to wait, that is the back-off factor. So how many time slots you have to wait, that is the back-off factor. So back-off factor, it is not fixed, it can vary, depends on the environment. So here the access control scheme, so one is the access class barring, ACB. ACB means, so here, so the base station is going to broadcast one number. So the devices, all devices generate a number between 0 to 1. So base station control, those who generated above 6 can transmit now. Those who generated above 0.4, now you can transmit. So that number base station changed, the access class barring factor. Then back-off factor, if you failed, okay, you have to wait 4 time slot, 8 time slot, 9. So that is the back-off factor. How long you have to wait, that also will change. If the traffic is heavy, back-off factor should be higher. If the less traffic, it can be less. So it should be changed dynamically. Then another access scheme is called distributed queuing scheme. So in the distributed queuing scheme, we have 2 parameters. One is depth, other one is degree. So here depth is 3. So that means here from 1 level, so it goes to 3. So here frame 1. So here frame 2, frame 3, frame 4. Then this goes here 5, 6, 7. This goes 8, 9, 10. Here how these 2 parameters decide is, okay, so here in the frame 1, So in the frame 1 is now allowed. So if the frame 1 is allowed, what is the next frame? So here, if the number is, so here it is 3. So this right hand side, so if you take here 3, so cyclically it should be this first one. So first one goes here. So that is this frame. So here 3, 1, 2, then again 3, 1, 2 like that. So here frame 1, then frame 4, frame 11. So then from here frame 11 it goes to the next level if you have next degree. So by this way, so we are going to have the depth. So here depth is 3. So degree is going to be here in the third level it is going to be 3 squared is going to be 9 frames are going to be here. So by this way, by defining these two parameters, depth and degree, so we can control the random access. So here in this case, so this one transmit first, then 4. So you'll have to wait 4th time slot. Then you'll have to wait 11th time slot. So these are the waiting time. Say here 4 to 11 only this device is allowed to transmit. So I will come back to that later. So now okay, so here we have 13 parameters should be changed dynamically. So because here we have the traffic, not homogeneous traffic, heterogeneous traffic. It's vary with the time. So when we take the dynamic optimization, so then we need machine learning. So the machine learning, so from the data means, so we will see in this problem what is the learning, what are the observations here. So then based on the observation, it is going to take the action. Action means the parameter values are going to be the action. We will see so how we are going to use the machine learning to solve this dynamic optimization problem. So here, if you see here, so why we use the machine learning? So because the environment changes dynamically, heterogeneous network. So here the channel state quickly changes. So then the network topology also changes, scheduling changes, everything dynamically changes. So we can't using the convex optimization problem. So therefore, since here we have model deficit, only option is machine learning. No other option to change the parameters dynamically. So how we are going to use the machine learning here? So this is the problem here we have. The problem that we have, this is a partially observed Markov decision process, not fully observed. Why partially observed is we don't have full information. So here why it is Markov decision process is, so here we have every frame. So here when you have every frame, we are going to have a state. State means, okay, so now, so 5th frame, for example, frame 1, time slot 1, 2, 3 like that. So in the 5th frame, state means, okay, during the previous 5 intervals, during the time slot 1, what are the 13 parameters? So then what are the action taken? So the action taken is 13 parameters, depends on the load condition. Time slot 2, what are the parameters? What are the action taken? 3, what are the action taken? So everything form a state. So at a particular state, so here the base station organize the transmission and retransmission, and base station receive the feedback. So what is going to receive the feedback is, okay, so one time frame. At the beginning, base station select these 13 parameters. At the end, it will receive the feedback. Feedback means how many preambles collided. how many preambles not utilized, how many established the connection successfully, how many devices, even though they established the connection, they may not be able to transmit because channel changes during the data transmission period, so data transmission failed. So how many devices they successfully established the connection and successfully transmitted data. So these are the 5 observations. So the base station observed. So then once it observed, next at the beginning of the next, according to this observation, it changed the parameters 30. So at the end, it will observe again. Then the next frame it will change. So here what we are going to have, so but we don't have the full observation. Full observation means we don't know how many devices select the same preamble and collided, we don't know. We don't know the channel conditions, we don't know. We don't know the exactly how many devices the ideal, so we don't know fully. So because of that, we don't have full information. This is a partially observed Markov decision process. So if this is a now here we are going to use the, so there are 3 main groups: supervised learning and unsupervised learning, reinforcement learning. Yeah. Again, not 13 parameters. I will explain in the next few slides what are the observation made. 13 parameters are going to be the action. Observation different. I will explain. The next slide. So here I can explain what are the observation, what are the actions. Here. So here the base station is going to observe these 5 values, observation. So that means at the end of a time frame, so how many preambles collided? How many preambles succeeded? How many preambles were idle? How many devices established the connection and successfully transmitted the data? So how many devices failed and waiting? So we are going to have backlog. So because during this time, so accumulated, previous time failed. So here we are going to have how many devices waiting. All these are going to be observed at the end of each transmission time interval. So these are the observations that we are going to make. So now the question is, so here, why we are going to use the, since this is a partially observed Markov decision process, we can use the reinforcement learning. So if you take the reinforcement learning, it is going to learn and make the sequence of decision. So here the decision are the 13 parameters. So how to select the 13 parameters are going to be the decision. So here the goal oriented learning. So what is going to be the goal here? To improve the number of devices successfully served. So that is the objective. So here the objective is, so whenever the number of devices successfully served increases, so we give the reward. So the reward is that the agent get the reward when the number of devices successfully served. So once it get the reward, so that means agent selected the correct parameters. That's what the agent get the reward. So now, because of this, it's a Markov decision process. So we are going to use the reinforcement learning. Wait, I will come back to the reward. So what is meant by reward? This is the reward. So reward function is the all three regions number of successfully served devices. So if more devices successfully served, then the reward is more reward. Sorry? So here action not established. To establish the connection, you have to select the parameters. So how many preambles for each region? What is the repetition value? What is the random access opportunities? Everything should be selected. If you don't select correctly, it won't establish the connection. Sorry? Agent take the action. Action means select what are the best 13 values based on the previous observation. So previously, how many collided, how many idle, how many succeeded, how many, based on the 5 observation, it's the agent will select, okay, these 13 would give the best reward. So if the agent does not select those 13 parameters dynamically, so device will not establish the connection, so all devices will fail. Here no supervise. Here no label data. Here just observation, action, reward. There are 3 things. Yeah. So here no label data. So here we observe the environment and we take the action such that the reward will be maximized. Reward is how to maximize the number of devices successfully served. So if you don't take the action properly, so then all devices will fail. They won't succeed to establish the connection. So here how the agent is going to select the action. So here based on Q learning algorithm. So Q means the quality. So Q learning algorithm, so here we are going to, the basic is we are going to have a Q table. So what is meant by Q table is, so here what are the all possible states? So during a particular time frame, so what are the possible states? Here we will have huge number of states. So if you have few number of states, generally if you have few number of states, in every state we can have a set of action. So according to that action, we can calculate the Q value. Q value initially is 0. Then using this Bellman equation, we can update the Q value iteratively. And we can prepare this Q table. This is, for example, say if you have 4 states. If you have 4 states and 4 action. So if it is in this state, if you take this action, so using this, we can calculate the Q value. So by iteratively, we can have this Q table. But here, the problem here is, here we are going to have huge number of states we are going to have. So therefore, we cannot use the Q table, we cannot use it. So what we are going to use here is, so this is the Q table. So initialize the Q table, choose an action, perform the action, measure the reward. Based on the reward, we are going to have new Q value in the table. Iteratively, we are going to update the Q table. So this is the Q learning algorithm, the basic. So here, so Q table is used to calculate the maximum reward in every state for every action. But when you take IoT application, this Q table is not feasible because here we are going to have huge number of states we are going to have. So therefore, what we are going to use the deep reinforcement learning. So not Q table. So deep reinforcement learning so the number of states depends on the number of IoT devices. So huge number of states we are going to have. So if you have huge number of states, this table is going to be huge. So the memory problem, so we may not be able to have this Q table. So Q table is suitable only if we have few states. So in IoT applications, we are going to have huge number of IoT devices. So the states, the possibilities are going to be very huge. So now the action here is the 9 parameters. So the combination of 13 parameters or 9 parameters. If you take the 9 parameters, we are going to have different combinations. We are going to have huge number of actions possible. So if you have 2-3 parameters, so few number of actions, combination of actions possible. But here we have 9, 13. So we are going to have huge number of possible set of actions we post. So therefore, preparing this Q table is huge. So it's not. So that's what we use deep Q learning, deep reinforcement learning. So that is. So here deep learning is we replace the Q table with neural network. So because the Q table we cannot prepare it. So here the neural network, what it is going to do, so here it is going to map the input state into action Q value pair. Say for example, to see this example here, say here, this is just one example. So here we have a neural network. So here neural network, so here we have the weight vectors we have. For each branch we have weight. So when we have one input state, so if you train this neural network, so if you feed the input state, it will give, so output, so action Q value pair it will give. This is just simple example. This is simple example. So therefore here, so a particular action, set of action give Q value 3. Another one gives 7. So therefore, so the base station will select that set of action because that gives the Q value 7. So because of that, so here we use the say here the state is going to be like this. Like this. So this is at a particular time slot. This is the state. So state means, okay, during the previous whole time interval, what are the actions you take? So here, so this A, so due to the memory size, we take only the last M naught time slot. We cannot take the whole time slot. Infinite we cannot take. So here we take, so what are the actions taken? So here, what are the observation action during the whole previous time interval form the state. So then at this time we cannot take all previous tens of thousands of time interval, we cannot take it because state huge number. So that's what, due to memory problem, we consider previous 10 time slots, previous 20 time slots we consider. So observation action form the state. Say for example, if you consider previous 2 time slots, so previous 2 time slots, what action you take? What are the 9 or 13 parameters? So what are the 5 observations? During the previous time, what are the 5 observations? What are the action taken? So observation and action taken form the state. So here this is the state at this time. Next time slot, state different, because during this time you are going to take certain actions, certain observations, so state will change. So this is the state. Yeah. So now the question is, okay, so now we are going to use the deep Q learning, because we cannot have Q table, we cannot iteratively prepare the table because huge number. Because of that, we are going to replace by the neural network. If you have the neural network, so it is going to map input state to action Q value pair. So because of that, we use the deep Q learning. So here in the deep Q learning, we are going to have some problem here. So that means sometimes, so overestimate action value, overestimate the Q value. So if you overestimate, it won't converge. So because of that, we are going to have double deep Q learning. So what is double deep Q learning? This is a difference. This is Q learning. In this Q learning, the Q value updated using this Bellman equation. So this is the new Q value, this is the old Q value, this is the learning factor, this is the reward, this is the discount factor. So here we are going to, from a particular state, we are going to consider all possible actions. Which action give maximum Q value we are going to select. Then minus the old Q value. So by this way, we are going to update the Q value. But the problem here is, so here we are going to have overestimate. Because of that, we are going to have double Q learning. So that means we are going to have 2 DQN, 2 deep Q neural network we are going to have. One to calculate this value, another one for this function, estimated Q value calculation. So for all possible values of A, which action gives the maximum Q value, for that one we use another deep Q learning network. By this way, we can solve this overestimation problem. So here sometimes the agent choose the non-optimal action for a particular state because it overestimates the Q value. So to solve this problem, so what we are going to do, we are going to have 2 deep Q neural network, one for this one, other one is the normal Q calculation. For this one separate deep Q network, so that is like this. So here we have, this is one deep Q network, this is another one. So to calculate the loss function, so by having 2 deep Q network, we can solve this overestimating problem. I'll come back to that later. Okay, so this is the Bellman equation for basic Q learning. This is the double Q learning. For this one, we use 1 DQ neural network. So now, so the question is, so here we are going to have multi-agent we are going to have. Say here we have 13 parameters, 13 agents we are going to have. Agent is a software. So here we are going to have 13 agents. So 13 agents, for every parameter 1 agent. So 3 region, every region 3 parameters. 9 parameters, 9 agent. So select 9 values. Then the 4 agent for random access control. So 13 agent. So 13 agent, how they select the optimum value? They are either cooperative or competitive. In this case, we are going to have cooperative. All agents works towards a common goal. So common goal is, so we have to increase the number of successful devices, successfully served devices we have to increase. So all agents cooperatively work together to increase the number of devices successfully served. So that means, we'll see here. So here, so the why we are using deep reinforcement learning here. So here the main thing is long-term reward. What is long-term reward? What is short-term reward? If you use the conventional solution, only during this time slot only we consider. Okay, this time slot, how to maximize the number of devices successfully served. But here, when you take the deep reinforcement learning, I will show in the next slide, we are going to consider the future. So that means, so not only now, the future after 100 time slot, also we have to serve the devices successfully. So that's what this deep reinforcement learning consider the long-term key performance index. How it consider the long-term? I'll come back that later. How it consider is this one. So here, the expected value of successfully served devices within these three regions, region 0, region 1, region 3, green, red, blue, all three regions, the number of successfully served devices. Here we have a weight factor, weight here we have. So this weight, so if you put k is equal to t, current time interval, so this is 1. Future, this weight is going to be less. So future, this infinity means future you may consider a big number. Infinity means just a big number. So we consider the future factor here. This factor gives to make the decision such that the future rewards will be maximized. So that is the purpose of this deep reinforcement learning, not short term, consider the long term future. So I will come back to this later. Okay, so now this is in the uplink, the process here. So here what is happening from a device, first one packet arrive. So you have millions of devices around the base station. In a particular device, packet arrived. Once the packet arrived, next one is the group determination. So whether blue or green or red. Once it determines the group, so then we are going to have random access procedure. So once we establish the random access procedure, so if it is succeed only, the data transmission here. So here we have different counters we have. So that is, so here random access channel opportunity we fix it. So then if it does not succeed within that number, we assume that it is failed. So this is the normal the execution procedure from a device once a packet arrives. So then determine the group. So for each group, so we have the random access procedure. So that is for that particular group, number of preambles, number of repetition factor, everything using that value, execute the random access procedure. If it succeed only, so data transmission occur. So here sometimes they succeed in random access, establish a connection with the base station, but here they failed. So we are going to have the scenario of these scenarios we are going to have. So that means preamble collided. So preamble collided means no random access succeeded. So succeeded preamble, so establish the connection. So the last one is establish the connection and successfully serve the devices. The finally succeeded. So these are the 5 observations. So base station observed at the end of each transmission time interval. So once it observed the agent, so here the problem is, so here we are going to have set of action. This is the observation. So this pi is the policy. The policy means, what is meant by policy is, so at a particular state, the probability to take a particular action. So that is called policy. At a particular state, what is the policy mean? What is the probability to take this action 1? What is the probability to take action 2? That is the policy. So here we are going to select, based on the observation, given observation, we are going to select the action such that long-term reward maximized here. So long-term average number of devices successfully transmitted data. So the long-term, so that's what here we consider the weight for future rewards. So now, so the observation here in terms of preamble, so here we can estimate the backlog using the method of moment. So method of moment is like this. So that is, say if you have the number of preambles a certain number of value, so how many preambles collided, succeeded, idle, so then we can estimate the load. Estimate the load means, say, how we can estimate. I can show you some simple example. It's not moving. Here. No? Yes. So using simple probability, we can calculate the, so you have the F is the number of random access opportunities if you have. So then you can find, so here if the backlog is n, so how many, what is the probability to succeed using simple probability calculation? We can calculate the expected value of succeeded preambles, we can calculate. So similarly, we can calculate expected value of collided preambles, expected value of idle preambles, succeeded preambles, collided preambles. Using simple probability equation, we can calculate. So now, Okay, so now after this observation, these 5 observation, so it is going to take the action. So that means, so here we have forget about the random access control, we take 9 parameters, 9 agents, select 9 parameters such that the reward will be maximized. So now the Q-learning action, so taking these, for each region, taking these 3 parameters, total 9 parameters, such that the reward successfully served devices within these 3 regions will be maximized here. So now, so this is the normal Q-learning, how to update the Q value. This is the old Q value, this is the new Q value. So this is the learning rate, this is the reward, this is the discount factor. So this is the all possible state, all possible actions from a current state to next state, which action give the maximum Q value. This is the old Q value. By this way, so the Q-learning update process happened here. So observe the environment here. This is the reward, normalized reward. So the reward is given to calculate, update the Q value. So then once you take the Q value, so action here there are, you can take the action, which action gives maximum Q value you can select, that is called exploitation. You can take exploration. Exploration is you can take a random action, not the action that gives the maximum Q value. So say this epsilon value can be say 0.1. So 10% of time you take random action. 90% of the time you take the action that gives the maximum Q value. So here, if you take the, in the deep Q learning, we have the loss function. What is the loss function is? The function of the neural network is to minimize the loss. The minimize the loss function is the difference between the target function and the predicted one. So we don't know the real target, so we can have the expected target. So this is the expected target. So this is the predicted one. So here the loss function, this is the stochastic gradient of the loss function. So by this way, so the deep Q learning is going to train the weights. So here we have 2 DQ and network I told you earlier. So one for to select the action which gives the maximum Q value, other one to calculate the Q value. So then we take the exploration and exploitation to take the action that gives maximum reward. So once it take the action, again it is going to observe the new observation. At the end of the time frame, it takes the new observation. Based on the new observation, so you know the what is the new reward. So this iterative process will continue. So this is the theta is the neural network weight vector. So how it is updated the weight from current time slot to next one using the stochastic descent gradient method. Sorry? This one. Okay, so here we have 2 DQ network to calculate this. So one is to calculate this one, other one calculate this one. So we have one to calculate the expected Q value, other one to calculate the this Q value. So here if you have just one basic Q learning algorithm, it calculates this normal Bellman function here. In the double Q learning, we have a separate neural network to calculate this separately and feed it back to calculate this one. So that's what here. That's what here we have. Here one DQN network. This is another DQN network. So using this and this, it calculates the loss function. Because to calculate the loss function here, yeah. So here, if you use just basic Q learning here, so we don't have double, so it is like this. The implementation of this. If you don't use the double just Q learning, this is the Q value update. So here, the Q value function, how it is updated here. So once you get the reward here, this one. So here the reward is fed back to the Q value function calculation. So then the Q value, this is the old value, updated to this new value based on this reward. Then it consider the all possible action values. So that means from the current state. So what are the all possible action it could take? Say the combination of 9. Say if you take one agent, so what are the action it can take? What are the action it can take? For example, if you take repetition value, for example, one agent repetition value, for example, it can be 2, 4, 2, 4, 8, 16, 32, 7 action possible, 8 action possible. So 8 action, for all possible 8 action, which action give the maximum Q value, it will select that agent. So here consider all possible 8 action and select which one gives the maximum Q value, it select that one. So for this one, to select this one, so we use a separate neural network here, like this. So the current state, so for all possible action, say if you have 8 actions, so that neural network give 8 Q values it give. So which so output is going to be action Q value pair. Input is the current state. From current state, so all possible actions, what are the Q value it will give? Because based on the Q value, you are going to select the action. Say for example, one agent, say the repetition factor, 8 possible action it can take. So for each 8 possible action, so it will give 8 Q value. So current state, this one. At this particular state, if you take repetition value 2, what is the Q value you will get? If you take 4, what is the Q value you will get? If you take 8, what is the Q value you will get? So for all possible action, 8 actions, what are the Q value you will get? You will select the action that gives maximum Q value. The state, I mentioned earlier, state is going to be determined by during the previous few time intervals, observation and action. So that means during the previous certain time interval, so what are the action you take? So previous time you may have take the action repetition value 4. Before that it may be 8. Before that it may be 16. Yeah. So the all previous actions and all previous observations form the state. So according to the state, the future action that you are going to take, 8 action, give the new Q value. New action and new Q value. Yeah. So you are going to select the action, which action gives maximum Q value. Say for example, the repetition repetition value agent. For example, repetition value 8, it gives the maximum Q value. So you select 8. Yeah. For example, if for 8, if you get Q value maximum, so then you select 8. Sometimes you will have to select 16 because it depends on the state during the previous time interval. So what are the observation and the action you took? State is formed by the previous observations and previous action for certain time slots. So the previously you selected, say for example, last 4 time slots, say low repetition factor. So that means, so channel condition during the last 4-5 time slot is good. So then the low repetition value will give high Q value. Then you take that action. So during the past few intervals, so channel is bad. So your repetition value is high. So based on that, this neural network will calculate what is the best action, the repetition value now you can take. Yeah, the repetition is the action. So here we have 9 agents. For each region we have 3 agents. The number of random access opportunities. Yeah. Yeah. So 9 agents. So if you take one particular agent, for example, repetition factor, so this A is going to be 8 values. So for 8 values, it gives 8 Q values, it calculates the neural network. So how this weight update in the neural network is based on the loss function. So the loss function is the difference between expected target function and the predicted one. That is the loss function. So we have to minimize the loss. So that means, so that predicted one and the target one should be minimized. So to minimize, if you are given a function to minimize, what you do, you take dy by dx and make it equal. So that's what here we have this equation. So this is the neural network weight, how it is updated using the stochastic gradient descent method. So the current vector minus, so this the learning rate, time, this is the gradient of the loss function. So by this way, the weights are updated of the neural network. So now, as I mentioned earlier, state form the previous actions and previous observations. So here the reward is to maximize the number of devices successfully served during in the all 3 intervals. So here all agents cooperatively optimize. So here we have 9 agents. So here 9 agents. So here state is stored in this memory. So here we have 9 agents. So they take the 9 actions. So here they do the observation and reward feedback. So then they, using the stochastic gradient descent method, these weights of the neural network will be updated. So this process will continue for next time slot, continue for the following time slots. Stated will be updated here. in the memory. So here the agent select the action based on the, now in the memory you will have new state because you are going to have last 10 time slots. So the last 11 time slot will be removed. Yeah. So now now we are going to see the traffic modeling. Yeah. Random access opportunity. So how many times one device could be allowed to try again and again? Say for example, if the channel condition is worse, that device will be allocated, okay, 10 times you can try. Yeah. Yeah. So if the channel condition is good, so it says okay, two times enough for you, like that. So it changed because of the state. Yeah. So state is the previous time slots action taken as well as the observation. So now, okay, after 5 minutes. Okay, well, fine. So now here we are going to have the bursty traffic. I mentioned yesterday about the pay as you drive situation. So how we are going to model it in the 3GPP standard, in the report they recommended the time limited beta distribution is the correct model, correct way to model the bursty traffic. So here we can model the bursty traffic using these two parameters alpha, beta, changing the parameters 3, 4, 6, 8, 3, 4, 30, 40. So here we can model the bursty traffic, heavy bursty traffic, light bursty traffic we can model. So because when we do the simulation, so how we can model the bursty traffic? So we use the time limited beta distribution, we can model it. So when we model it, so here, so we consider the deep Q network. So we consider 3-layer neural network. Each layer we have 128 linear rectifier unit. So to do the simulation, we use the Python. In the Python, you can use the neural network library, Keras library. In the Keras library, you can change the number of rectifier units, number of layers, everything you can change. So built in the open source library. There are several other libraries also there in addition to Keras. Then you have TensorFlow. There are many other libraries available. You can take it in Python program. So here you see, so when you take the action, say here, this number of preambles. So that agent can select action, these 4 possible actions. So 12 preamble, 24, 38, 48 in a particular region. So other agent, the repetition value 1, 2, 4, 8. So one of these 6 action it can take. Random access opportunity 1, 2, 4. One of these 3 actions. So number of actions for those agents. So here 3, here 4, here 6 action it can take. Yeah. So here we consider the transmission time interval. The frame, one frame is 640 milliseconds. One frame, that is one resource block. Here frame. Yeah, so 180 kilohertz times you have the frequency domain 180. Time domain 1 millisecond, 1 resource block. Here we have 640 millisecond for data transmission, then the physical random access, everything we use it, 640. So here we consider the learning rate and discount factor, all these factors. Then what we found, So maximum transmit power for random access. Yeah. By the IoT device. Yeah. Yeah. This is the base station broadcast power 35 dBm. So then we use the path loss exponent also for. So here we consider base station at the center. So all the devices are within the 12 kilometer radius. So we did 1000 training episode. So when we take the numerical results, so you can see this is the, we simulated using the time limited beta distribution. So if you take, this is the conventional load estimation approach. So they failed during the bursty traffic. But this, when we have these 9 agents, they succeed here because they dynamically change the parameters every 640 milliseconds. So by changing the parameters here, how they change here is like this. Say if you take the repetition value, so this is the red region, this is the green region, this is the blue region. You can see, say if you take the fixed value or load estimation value, so they use some fixed value. But here the load estimation value, they use fixed repetition value of 8. Here repetition value fixed 4. Instead of having fixed 4 and 8, this blue line 4 repetition value, green repetition 8. But here the repetition value changes, here 4, 16, here 8, then during this peak burst time 8, then go to 16, come to 4. So dynamically changing here between 4, 8 and 16. Every 640 millisecond it's changing. So these are the frame number. So here say if you do the simulation for 10 minutes, so within 10 minutes, if you divide by 640 millisecond, you can get the number of frames. So here if you see, this is the random access opportunity. This is the multiplication of the random access channel multiplied by number of preambles. So here 48. So here 196. So here you can see this load estimation one, during the bursty traffic, the blue and green, they reduce the random access opportunity because collision occur. But this one succeeded because it reduced the repetition factor but increased the random access opportunity. Dynamically changing here, this reduce here, this one increase here, this one fixed and reduce here. Increase the number of random access opportunity because collision occur, but reduce the repetition value. So because that combination gives the maximum reward. So here this one is fixed, this is reduced. So this is the benefit. So if you want to learn more, so you can refer these papers. All the derivation, technical details, all are there. Yeah, because so here you see, so here repetition value less, random access opportunities increases because of the bursty traffic, collision occur, so it increases the random access opportunity. So in the group 1 and group 2, so here the load estimation, so it reduces the random access opportunity, so that's what they were not able to succeed. Yeah, so So this combination, so that is reduce the repetition factor, increase the random access opportunity during the bursty traffic period, give them more reward. So if you take load estimation, they fixed. Repetition 4 and 8, they fixed. They are not changing. So then if they are not changing, so then they won't succeed. So here, the number of repetition in the light traffic in order to improve the SNR and reduce the failure here. In the heavy traffic, to reduce the scheduling failure, they decrease the repetition value. In group 1 and 2, so here load estimation decreases to reduce the scheduling failure. So that causes the overall low throughput. That's the reasoning. Sorry? So for every region, say for example, in this region, so here this one is fixed, but this dynamic one increase the repetition value during this region, because in the red region, so here the repetition value this is not 1, this is not 1.5. No, not 1.5. This number is wrong. Maybe 5. So sorry? Okay. Okay. So